Thank you all. Good morning, everyone. We will start with the technical session today, which I am going to take on innovation of novel materials in manufacturing sector.
Yes, sir.
Yes. Okay. So till now we have heard about many novel materials and nanomaterials, in which we were learned many things about. Even in 3D printing also, Sir has taught many things. What were the new materials are coming into various field. So such things also Sir was said. NIT Warangal Sir, Professor Ravi Kumar Sir, and also Professor Ramesh Sir. He also shared many things about the electronic materials, novel materials, MEMS, microelectronic mechanical systems, and biomaterials. We have learned about the biomaterials. And in manufacturing sector also, we used to come across various materials in manufacturing sector. In foundry, if you see, there are so many materials that are available to make like castings in a very good manner. So in a very good manner. So for example, for green sand casting, if you see, nowadays they are using lot of the natural materials which are available in the market. For example, molasses, and about the various waste materials. Nowadays they are making the waste materials like coconut fly, and also coconut flies, and also this cow dung and fly ash. So all these waste materials are nowadays they are using in foundry to make the mold to be strong, so that we can get the desired casting in a very strong manner. So such a way they are now utilizing various natural materials which are available to make the castings to become very strong. So now we are going to see in our today's talk about the manufacturing of the various metal composites by using the various natural materials that are available. Okay. So now in the present talk which I am going to discuss about the we are going to discuss about one alloy, that is A206 alloy, which is nothing but aluminium copper alloy. So this aluminium copper cast alloy is very, very important in aerospace industries, and also automobile industries, as well as this marine industries also. Because for making the thin castings, it is very difficult for us to manufacture thin castings. Because if you see the aerospace, if you see the aircraft bodies and all, they are actually very thin in shape. They are very thin in size. So to make such thin size castings, we require we should require suitable casting techniques. But by with the help of the present day castings, like about many castings, sand casting, investment casting, steel casting, and so many other techniques are there. But the problem with the thin casting is to improve the quality of the casting. That means if the quality of the casting is not improved, then what will happen is that the casting will have some defect, and the casting will not that the casting product casted product will not become that much will not have that much strength. So our objective is to improve the strength of the casting. So in order to improve the strength of the casting, we need to improve the strength of the mold. So the question is how to improve the mold. So to improve the strength of the sand mold, we have to add we are trying to add various materials such as fly ash, and we used many coatings. I am going to explain what are the coatings that we are used, and also the various coatings to improve the strength of the casting, and also various materials to improve the strength of the mold. If we are able to increase the strength of the mold from which the casting has been made, then the casting strength also will be increased. So in the present lecture, we are going to discuss about all these things, how to improve the casting product strength. Okay. So let me tell you, in this talk, we are going to do what is the green sand mold system, and what are the investigations done on the fluidity, and how we are validated the the product with by studying the mechanical properties, and what is the technique that we have used to find out the optimal properties, that is Taguchi based method, and also technique for order preference by similarity to ideal solution, which is also called as Topsis method, and what are the literature review that we have taken, and what was the industrial motivation, what is the discussion, what is the gap areas, and these are things that we are going to the experiment that has been carried out and optimization that has been carried out on the green sand mold, and the materials that we have used for fluidity testing. So these are all things that we are going to discuss. So, and what are the various coatings, mold coatings that we have used in order to improve the fluidity, and what is the grain refinement that we have used, and what is the effect of that grain refinement. Okay, there are so many grain refiners available in the market. Like yesterday, Sir was saying about the graphene, which also use it to improve the grain refinement, use it for the grain refinement, and titanium, boron, so, and also niobium. These are all the materials which are available in the market to improve the grain refinement of the material. So what is grain refinement, that we will see, and also what is the scrap that is affecting on the fluidity. So and metallographic this one. So then we are going to study what is the effect of the composition of the molten metal on the mechanical properties, grain refinement of the mechanical properties, and what are the effects of the process parameters on the mechanical properties. So that is all. So yeah. So let me give you a brief introduction about the green sand mold system. You know, foundry is the one of the ancient method in metal forming. According to the data that is available, production data, 70% of the casting defect are arised due to sand mold properties. That means if you are able to improve the properties of the sand mold, then automatically you will get the good strength in the casting. So most of the common defects that we found in these castings are porosity, that is the major problem, and surface finish is very, very poor, and dimensional variation, shrinkage, cavity, scabs, rat tails. You might have studied in your subject what are the various casting defects. So these defects can be minimized by a proper control of the properties like green compression strength, permeability, hardness, and bulk density. So these are the main properties which decides the properties of the mold, sand mold. And not only that, nowadays the materials we see they are adding in the foundry sector to improve the sand mold, such as wood floor, sea coal, coal dust, husk, fly ash, molasses, etc. They have been used to enhance some specific desirable properties of the molding sand. If you have a low green compression strength, that yields a casting processing, poor surface finish, dimensional accuracy, and also it will create porosity. Similarly, low permeability may be a cause for the blowhole and Misran type of defects. Misran type is nothing but the fluidity. The ability to flow the metal will be decreased. If the ability to flow the metal will be decreased, then there will not be complete casting. There will be some defect, and that defect is known as Misran defect, or we can call it as fluidity defect. And one more thing that we can talk about, that is the bulk density, which is related to the flowability of the molding sand. So in such a way, there are so many the green sand mold properties are influenced by a large number of parameters, therefore, which are controllable to varying degree in our foundry. So that is why, being a foundry man, uh, he should be in a position to sell the molding composition to get the substantial increase in sand mold properties, which in turn leads to the quality castings. So quality castings depends upon the mold properties. And in order to obtain the optimum economic production with green sand mold properties, we need some professional and governing staff is familiar with the best method for control and operation of the green sand molding. So till now, actually, there are so many optimization methods are used to produce the quality of the green sandy castings. They designed so many. They designed they optimized the casting process parameters by using various optimization technique, regression analysis, Taguchi method, etc. So, what is Taguchi method? We don't require. And actually, with the after making the sand mold, so we are going to talk about the A206 alloy, that is aluminum copper alloy, which has been made by using the optimized properties of the optimized sand. Optimized sand means we have taken certain parameters and we have made the green sand mold, and in that green sand mold we have made the casting A206 alloy, and that the problem with the A206 alloy, aluminum copper alloy, is actually while casting the aluminum copper alloy, so main defect that we found is that this one, the fluidity of the melt is very important. Misran is the major defect in the A206 alloy. So because this A206 alloy will be generally used for making thin wall castings. And it is also called as a long freezing range alloy. So that is the reason why this Misran defect will come. So this is overcome by using the various mold composition. This is how the Misran will happen. So you can see the Misran in the turbine blower. If the casting is incomplete, if the metal flow is incomplete, then we will find this kind of defect, that is Misran defect. You can see in this one also, a Misran is called when the metal is unable to fill the mold cavity completely and thus leaves unfilled cavities, right? You can see some unfilled cavities, you can see, and this is what we known as what we can call as the Misran defect, or we can call as fluidity defect. So long thin sections are subjected to this defect. Long and thin sections are subject to this defect and should be avoided in casting design. By suitable design, we can try to minimize this defect. I've already told A206 alloy, it is actually belongs to the aluminum copper alloys, which are widely used for manufacturing thin wall castings. Manufacturing thin wall castings of automotive, aerospace industries, due to what is the reason? Due to high strength to weight ratio and virtuous mechanical properties. It has very good mechanical properties and high strength weight ratio. Okay, when you talk about the marine field and also aerospace industries, they will think about high strength and weight. They need less weight and more strength. So, however, castability of the mechanical properties of the A206 alloy depends upon the capability of the mold called fluidity. Okay. So there are several challenges in the casting process, particularly thin wall casting. So smooth filling with good flow properties are very much essential. Right? Mechanical properties of the A206 alloy are very attractive for structural components since they combine high ultimate tensile strength, good ductility when properly cast. So the important application of the A206 alloy are aerospace, military applications, structural casting, trucks and trailer, and gear and pump houses. So they have got huge number of applications. So the technique that we have used to optimize the casting process parameter is Taguchi based gray relational analysis. Okay, because this is the optimal process parameters selected not only to process quality but also to be least prone to the deviation of environmental conditions and other noise factors. So several experiments needs to be carried out when the number of process parameter increase. So naturally, when the number of process parameter increase, we need to carry out multiple experiments, and also it is a tedious task. So to reduce such a tedious task, then we use the optimization techniques. So in present this particular research, we have used the Taguchi based gray relational analysis technique. So you know that some of you know about Taguchi technique very well, because some of you are from manufacturing background also. We use so many orthogonal arrays to study the total process parameters, and to study the quality characteristic also by using the parameter called signal to noise ratio. This I will explain further. Okay. So SNA ratio will decide the quality characteristic of the casting product. So lower the better, higher the better, and nominal the better. So for us, actually, we require the mechanical properties to be high. Mechanical properties to be high. So we will take SN ratio is higher the better. Higher the better mode. So, and also if there are multiple responses, uh, then what we do, we have to convert that multiple characteristics, multiple quality into a single characteristic, and that is what we do in the gray relation analysis, to know the grade and to note the quality, single quality characteristic, the grade, and finally rank, and which composition of the material is giving us the best quality product, or we can say in which composition of the material we are getting the more strength. So that is what further. And TOPS is also another technique which we have used just to compare the both the gray relational analysis and this technique. And we suggest, finally we are going to suggest which method is useful or suitable for the better optimization of the composition. Okay. So many literature review has been carried out on the green sand. Okay. So in 1974 onwards, this research has been carried out. Of course, even before that also, they have applied the statistical design of experiments technique to study and control the properties of the green sand and resin bonded sand systems. However, the effect of the sand grain size and important property permeability were left out in their analysis. Okay. So, and Karunakaran et al. 2014, they also found the quality of the aluminum castings could be produced by using fly ash, which effectively replaced 24% of the molding sand in foundry, which in turn leads to cost-effective quality. So they have also studied the permeability, mechanical sand properties of the green sand by adding this fly ash and sugar cane, molasses, etc. Okay. So these are the literature review. The various people they have carried out. In 2012, the optimum process parameter value for multiple objects, namely green compression strength, permeability, mold hardness, they have used the genetic algorithm and particles of optimization, etc. to find out that one. So, and in 2013, the blackstrap molasses they have used as a core binder to improve the sand, to improve the mold properties like permeability, green compression strength, etc. Yeah, fluidity also, if you see, fluidity is the Misran defect. There many studies has been carried out in this particular field also. Let me. And then coatings also will affect will bring a positive effect on the fluidity. So several researchers have they carried out the research on the coatings, mold coatings, to improve the fluidity, to improve the Misran defect. Okay, so What is the motivation? That actually present day boundaries is quality mold sanding mixture is very much required. Quality molding sand mixture. So this can be achieved by the set of input variables which are required for us to achieve the desired levels of output, that is mold properties. So mechanic sand properties, green compression strength, permeability, hardness, bulk density are the major sand properties that are there. So, and when it comes to the aluminum alloy casting, the industrial demand for thin wall castings is in aluminum alloys plays a vital role. Plays a vital role in producing lightweight castings and provide new opportunities for aerospace and automotive industries in producing lightweight structures with good mechanical properties. Okay, so these opportunities can only be realized when the foundries are confident in their ability to produce thin wall castings. So production of thin wall castings is constrained by the fluidity of the molten metal. Therefore, the primary issue that must be addressed in producing thin wall casting is the fluidity. So fluidity of the molten metal is of the significant importance in producing the sand castings, particularly making complex shape castings. Okay. So in that is why in this present investigation, so we have used the scrap also and mold coatings and other elements like nickel also we use to improve the material composite material that yeah, we can say metal matrix material A206 alloy. Okay. So is actually why we have to study. What are the research gap in this particular field? That is, several studies they have been conducted on molding sand, binders, and additives, which have been widely reported in literature. However, the influence of the molasses and fly ash, along with the grain fineness number, bentonite, moisture, and degree of ramming on the molding properties of the green sand has not yet been investigated, and this study has been carried. Although there are several researchers, they made an attempt to optimize the green sanding process by traditional Taguchi method, but few have used the multi-objective optimization technique. So, and it is essential for us to determine the set of input parameters to ensure set of desired mold properties. So, it has not been solved completely and proficiently. So, many others have noticed that the pouring temperature and grain refinement play a significant role on the fluidity of the aluminum alloy. So they made an attempt to improve they made an attempt to study the influence of pouring temperature and alloying elements and grain refiners, but no report or literature was found on the influence of the pouring temperature and molding coatings and scrap on the A206 alloy till date. So therefore, to simultaneously AFS and grain fineness number, AFS and grain fineness number, and also molasses, etc., to improve the fluidity. So we should not. So we do. And also aluminum, titanium, grain in combination with various process parameters such as scrap, nickel, etc., and fluidity using coated thin cross section of A206 alloy has not been investigated till date. So our objective is to improve the grains and mold properties by various input variables and getting the optimal combination from that one, and also doing finding out the fluidity and mechanical properties of the A206 alloy, and also studying the effect of the mold coatings at 3 different pouring temperatures, etc. And then by using grain refiner in combination with scrap, so and design of experiments, and then casting of the fluidity by varying these process parameters. Similarly, we are going to study about the influence of the pouring temperature on the fluidity, and also study of the influence of pouring temperature and grain refinement on fluidity and mechanical properties of the A206 alloy. So ultimately, we are going to enhance the fluidity of the thin cross section by using optimization techniques based on this one. So various methodology were affected that these are the various tests that has been carried. So this is actually the sand equipment we can see here, and this is the sand muller we can say, in which we are going to, in which actually the sand muller is used to mix the sand with various sand additives, like we have added fly ash, and we have added molasses, and also bentonite clay. So with variable proportions we have added, and we made the green sand with the help of sand muller. So after making the green sand, then we made the sample out of this sand, out of the sand composition, by using sand rammer, we can call. So with the help of the sand rammer, we will make the sand sample, and this sample is used for the testing. So to test the permeability of the sand, to test the tensile strength. So tensile strength is used to tensile strength, and also to find out the tensile strength, we will use this equipment, and this equipment is known as universal strength machine. And all the shatter index also has test also was carried out to know the this is actually yeah, that is what the methodology that has been followed out. Okay, so yeah, you can see this from flow chart. What are the various sand process parameters that we have used to quality improve the quality characteristics of the sand mold, and did the extensive literature survey and the selection of the various process parameters which are affecting the green sand. Okay, and these are the binders that we have taken, and we have used the optimization technique, and these are the sand additives, and we make the sand sample, sand sample out. These are the dimensional sand, and this for finding out the sand properties, and using the optimization technique, and optimization technique doing ANOVA is actually used to find out the contribution to find out the contribution of the various parameters and interpreting this. This is actually minerals. So actually, this is the cause and effect diagram that we can see. By using this diagram, we can see maximization of the properties. What are the machines that we use to increase the strength of the green sand mold, and what are the tests that has been carried out? Okay, and the methods, and also materials: sand, additives, fly ash, water, bentonite, and binders. These are the, so objective is to improve the green sand properties. Yeah, these are actually the input parameters that we have chosen in the range of this is the range, and these are the level of factors, means these are the level at which we have added the materials into the sand to improve the properties. Grain fineness number, the level is 53. So grain fineness number also we have calculated with that sieve analysis, which actually with the we have used this sieve analysis to find out the grain fineness number of the sand, and the water quantity, how much to be added, and molasses, how much percentage of the percentage by weight, right, to be added, and bentonite, fly ash, and degree of ramming. So while making the sample, how many with how many rams we can how much of degree of ramming to make the sand sample. So that is what. So degree of ramming, this one. Okay. So now yeah, this is actually the we have used L18 orthogonal array, and we have found out the green compression strength, and these are the actually the responses. Green compression strength, permeability, bulk density, mold hardness, shatter index, etc. So these are the various properties that has been obtained by adding these things in various level. So now, so this is actually the procedure for Gray relational coefficient and Gray relational gate. I don't need to explain all this procedure because it is the technique. So yeah, these are the actually by applying all these formulae, then first in this one first we have to do the normalization. Then first we have to do the normalization. We have chosen the larger the better characteristic, and we did the normalization. Okay, and then we'll find out the deviation sequence, and after finding out the normalized data is this one, and then this is the gray relation coefficient, and from this gray relational coefficient we will find out the gray relational grade. So that is what is, these are actually the normalization, and after normalization we will find out the gray relation coefficient. This is all we have found out from the responses that we have got. Okay, and then gray relational grade. Okay, gray relational grade, and based on the gray relational we will do the ranking. So if you see the ninth experiment, what is the ninth experiment? As for ninth experiment, yeah, ninth means this one. If you see at this particular composition, we see that at this particular composition, level 1, level 3, level 1, level 2, and level 1, level 3. What is ABCDEF? ABCDEF is grain fineness number. So level 1, level 2. So at these particular levels, we found the, yeah. So this is the level at which, this is the composition at which we have got the best properties of the grain sand, we can say, and that is what the gray relational grade decides. Okay, so now after that we have carried out the larger the larger the gray relational grade, the closer will be the product quality to the ideal value. Therefore the optimal levels of the grain sand is A1, B3, C1, D1, E3 and F1. They are represented in the table 5. Okay, so see, so A1, B3, C1, D1, E3, okay, and F1. So you see, this is the main response table, and then we have carried out the ANOVA analysis with the help of the Minitop software. So we get this. See, so the B, what is that B? That B is the factor, water percentage, and then yeah. So B, and after followed by the D, and then F, this one. So this, what is B, D, and F? This one you can see. Okay, water and bentonite and degree of ramming. So these are actually the influencing process parameters to improve the. So what is the maximum percentage? That is water. So moisture plays a very important role to improve the property. So we may add many other materials like bentonite clay, corn flour, yeah, coal powder, or fly ash, or so many other products, but the water plays, moisture plays very important. So because that is the binder basically. So that is what. So and then the optimal process parameter combination we have got at grain fineness number 75 and water percentage 6%, molasses 2.25, and this is the optimal composition. So and based on the analysis we have got, so water content contributing 62.73% as the strongest influence in comparison with the other processes. Okay, and later we have confirmation of the experiments has been carried out. Then we found that gradation gas is increased 22.25. Okay, then same on XRD analysis we have carried. Now we will come to the fluidity of the A206 alloy. So this can be improved by of course, and now we have optimized the green sand properties. Now we have come to improve the thin wall castings fluidity of the A206 alloy. So what I told, the problem is mold filling, that is misrun defect, or we can call it as fluidity defect. So we have added various coatings. Graphite, soapstone powders are mainly used as sand coatings in the present investigation, right? So what is actually the composition of the A206 alloy? You can see copper percentage is 4.25, and of course these are the other miscellaneous materials will be there, and aluminum, mainly aluminum, copper. Aluminum is 99.7, aluminum after copper, remaining percentage will be out of aluminum copper alloy. If we see, aluminum is the major one, and this copper is the second, and remaining are very minor things. Okay, so we have used the aluminum, pure aluminum, and made the A206 alloy. Okay, and this is actually used for testing the fluidity. See, 2 mm, 4 mm, 6 mm, and 8 mm thickness of the the thickness of this cross section, because actually we need to find out mainly the fluidity of the thin cross sections. So to know the fluidity of the thin cross sections, so 2 mm, 4 mm, 6 mm, 8 mm, we have taken 4 cross sections of different thickness, and this is the mold we have made with the help of this pattern. And see, this is what the mold cavity, and we have used that optimized sand for the mold, sand mold, and made the castings. Okay, so first we have done the casting without coating, that means uncoated, at the 3 temperatures, 700 and 750 and 780, and graphite coating at 700, 750, 780, and soapstone powder coating 700, 750, 780. So these are the pouring temperatures, and the fluidity length that we have obtained at different temperature is this one. So, and after this one, then we have studied the microstructure, and we found out the grain size, average grain size, and the average grain size is this one. Okay, different different average grain size plus 3, and mean grain size is this one, and this is what the standard deviation of the. So what we found is, without mold coating, the pouring temperature is as shown before. Figure 8. Microstructure of the fluid specimen directly poured into the test mold, and this one. Yeah, graphite mold coating. Let me explain. A highly suitable and appropriate, significantly non-porous and gentle mold surface can be produced by the graphite mold coatings. So that is the reason why it is suitable for manufacturing ferrous and non-ferrous castings also. They will use this graphite powder. So what is the reason? It increases the wetting angle between the melt and mold, helps to resist metal penetration into the mold, and increases undressing during shakeout. Okay. So yeah. So we did the XRD analysis of the graphite soapstone powder also. You see, the SiO2 peak is more, then that is representing that silicon oxide is more present in the graphite powder. So that is the reason why we use this for many we used to make we use this coating for the making of the ferrous and non-ferrous courses. So that is why we have used it for A206 alloy also, with the advantages we have seen here. So it increases the wetting angle between the melt and mold, and resists the metal penetration into the mold. So this is the XRD analysis and SIM analysis that we have carried on the graph. And also soapstone powder, why we use is actually it is obtained from the hydrous magnesium silicate mineral. It is extensively used as a stuffing material, having more hardness value as 1 and density 2.6 to 2.8. It is used in many uses because low hardness, high melting temperature, and sufficient chemical inertness and adhesion capability, that means surface coating, and high thermal conductivity. And it improves the cracking resistance and adhesion and barrier properties. So the graphite and soapstone powders have the almost similar composition but different particle size. So with reference to the XRD analysis, the soapstone powder coating used in present investigation, particularly silicon oxide, aluminum oxide, and magnesium oxide, and ferrous as. Okay. So, and then we have carried out the SEM and EDAX analysis for soapstone powder also. This is what that we have obtained. So yeah, these are the casting that has been made with the help of coating. So with uncoating, and if we do not use the coating, then the castings that are obtained like this, you know, and the corresponding microstructures, we can see there are a lot of what I say, dendritic these dendritic grains, and second stand for aluminum copper, and third one is globular grains. Okay, so for this uncoated specimen at various pouring temperatures, 700, 750, and 780. So yeah, initially. So then after that we did experiment with graphite coated green sand molds also for that optimized sand. Then we have got the values for the three different temperatures like this, uncoated and the graphite. See the difference, how much fluidity increased by using the graphite coated sand mold. Okay, so this is how the casting of 780 degrees centigrade. So this is how the fluidity increased. We have compared uncoated and graphite. So then one thing is observed is that fluidity was increased with increased cross section. Because naturally, if we go according to the formula, also if we increase the thickness, as soon as if thickness increases, the fluidity also increases because it will get more space for the cooling. So that is that is the reason why so 8 mm cross section we found the maximum fluidity, and yeah. So these are the corresponding micro structures we see for the graphite stone powder. Now, influence of the pouring temperature and the fluidity by soapstone powder, coated green sand molds. So soapstone powder coating mold at 3 altered temperatures has been carried out. Okay, and the fluidity is further increased from 76.1 centimeters to 82. So the table is given here. Okay, so 700 uncoated and soapstone powder. Okay, this one. So percentage of the increase in fluidity is this much. So the best composition that we have got in soapstone powder only. Okay, so because of the high melting point and high resistance and all, the fluidity increase is more as compared to the uncoated and graphite. So soapstone powder has given the best results as compared to the previous coatings. Okay. So see in this one, the more we see at 750 degrees centigrade, we see the more globular grains. You can say more equiaxed grains. If the equiaxed grains are more, then the material will be more strong. So the resistance effect. It was observed that through experiment, the fluidity length increases slowly with the increase of the cross section along the reason was the time required for the solidification of the metal to fill the mold cavity might increase as thickness of the cross section increases. So as thickness of the cross section increases, time required for the metal to be solidified also will be increases. So fluidity of the mold is soapstone powder mold was higher as compared to the fluidity in the mold with graphite coating and followed by the sand mold without coating. Okay. So these are the graphs that is obtained for various pouring temperatures. Okay. And the best one we see the soapstone powder coating, and at 750 degrees centigrade, and this is at 780 degrees centigrade. So this is what to convey. So graphite and soapstone have nearly similar composition, which is helpful to study the particle size coating effect on the surface quality of the A206 alloy. And also A206 alloy attended the soapstone for molding was higher as compared to the graphite mold coating because the contact angles are large. Consequently, the wettability of the mold when using molten aluminum is very low, and hence the fluidity in the thin cross section should be improved. So more globular grains are obtained at 750 degrees centigrade. So the fluidity length has been increased by influence of pouring temperature in the range of 700 degrees centigrade to 750 degrees centigrade for both the graphite, soapstone powder mold. So the reason might be due to increased supercooling and nucleation. So then we'll come to optimization. So we'll come to the optimization. Optimization of the various process parameters of the casting process parameters to improve the fluidity and mechanical properties of the A206 alloy. So what are the various casting? We have taken the grain fineness number, one process parameter, and also why we have taken to investigate fluidity. Moreover, and then the molasses and effect of the grain refiner, aluminum titanium and aluminum nickel, and also the nickel. These are the process parameter that we have chosen in the range of this one, and we have designated these all the parameters like A, B, C, D like that, and these are the level of factors that we have used. And again, we have carried out the same experiments of same process that we have followed in the sand optimization. We have followed the same optimization process in casting also. Okay, but the process parameters are different. Okay, so these are the properties, and this is the fluidity length that is obtained at various levels. So from this we can see the maximum fluidity that is what applied. Okay. So yeah, these are the castings that has been made with various temperature at various temperature. Okay, and then we have taken the sample from cross section 8 this thing, and we have made tensile test specimens to carry out the mechanical properties, tensile strength, etc. And then we have carried out the mechanical properties like Vickers hardness and Brinell hardness. Okay, so these are the situations. So, and when we by using the Gray relation analysis technique, we did the normalization and we found out the Gray relation coefficients, and these are the Gray relation grade. So in this one we see the third one is shows the grade 1. That means this is so. If we do the if you do the mean response analysis overall, this will you can see the star mark. So grain fineness number at one level and molasses at one level, and also this grain refiner at third level, scrap at level 1, and this aluminum nickel at third level, and also pouring temperature. So this is what after that we have carried out the ANOVA of the experimental result, and this is the percentage of contribution. You see the maximum percentage of contribution is F. So what is that? That is the pouring temperature is plays main vital role in increasing the casting quality, but by considering all other parameters, right? That's okay. And then that is the maximum contribution, and after that the grain fineness number also plays the maximum contribution portion, and then B is the molasses. So grain fineness number, molasses, and pouring temperature are playing mainly vital role to improve the quality castings. Yeah. So these are the actually this one graphs you see here. Okay. The SM ratio graphs and effect of pouring temperature. The linear relationship between pouring temperature and fluidity describes that increasing pouring temperature causes delay in the nucleation and growth of the fine grains at the tip of the molten metal in the tester. Hence, the fluidity then increases. He has given the reason why pouring temperature increases the fluidity, right? So it delays the nucleation and growth of the fine grains at the tip of the molten metal. So that is the reason why the fluidity length increases. And also addition of the grain refiner. Actually, it increases the grain size. If grain size, it sharpens the grain size. Increases means it sharpens the grain, and it makes the grain in globular size. And if the grain becomes in globular size, that means equiaxid size, then naturally the fluidity will be increased, and the quality of the casting will be improved. So that is what we observed in sixth experiment, where we found that the fluidity length is 98.20. Okay, and the corresponding pouring temperature is 700 degrees centigrade, and grain refinery is this one. Okay, 2.58%. Okay, so we carried out the microstructure also for the optimized this one. So we have got this type of microstructure. So, and if you see the micro hardness value for the second number of casting from the L18 orthogonal is 85. That was the higher, that was found to be higher at the condition of pouring temperature 750 degrees centigrade, and grain refiner at 1.5. So similarly, it was examined that micro hardness value 76 obtained for third number casting at the condition of pouring temperature 780 degrees centigrade, and grain refiner is 2.58%. What the reason might be due to the interdendritic eutectic mixture noticeably reveals the larger amounts of the aluminum copper intermetallic phase between the dendrite arms, which seems to be the result in the greater hardness values obtained for the A206 Li as shown in figures. Okay. So, and we have carried XRD analysis also. Yeah. So, uh, this is for minimum hardness, and here the maximum hardness, and the reason, and the XRD analysis for the optimum fluidity sample has also been carried out. So this is how this has been obtained. Minimum hardness and maximum hardness we have carried, and this is maximum hardness. Okay. So yeah, so at that sim analysis for optimal conditions of the um, tensile strength, tensile specimen. So you see the voids and dimples, ductile fracture, dimples. So this is the this one. Yeah. You see, this is the cavity and dimples. This is the one. And finally, we have carried out the microstructure. We see the grains are in the form of globular, means equiaxial grain type structures. Therefore, we can say, so modified green sand samples consisting of various percentage of molasses and yeah, molasses and fly ash into sand mix changes the properties of the green sand such as permeability, green compression, dry compression considerably in comparison with the Cornelius gray forest green sand. So we have compared with that one, and we found that the mechanical sand properties of the green sand is better than that one. And Taguchi based analysis also reveals us that optimal parametric combination at 75 GFN, water percentage is 6%, molasses at 2.25, and bentonite at 8, and fly ash at 8, and degree of framing is 4. And 62.73 by doing NO analysis, water contributing 8%, and bentonite has an effect of 14.06, and followed by the degree of framing. So confirmation of the experiment, and SIM and XOD analysis, which is found that maximum amount of the silicon oxide, which is the reason for the enhancement of the physical properties of the sand. And also by using the fly ash and bentonite, we can say molasses also, we can say bonding strength of the strand will be increased, hence the properties are improved. Okay. So pouring temperature plays the main role, and soapstone powder coating also main role to improve the fluidity. So also the present investigation results that found remain that a reasonable enhancement of the fluidity can be obtained by using mold coatings like graphite. So SEM XRD analysis and EDAX analysis has been carried out, and graphite and soapstone powder coating have nearly similar composition, which is helpful to study the particle size coating about that. So A206 Li attended by soapstone powder molding was higher as compared to the graphite mold coating, and because the contact angles are large, A206 Li was increased fluidity with the thickness of the cross-section channels, and also the technique of the cross-shaped fluidity test was reproduced to improve the scattering range of fluidity test. The fluidity was improved significantly by grain refining, especially at lower pouring temperatures. So these are actually the result. Aluminum copper scrap does not have a significant influence on fluidity and high protein. Therefore, it is recommended to the castings industry that scrap addition of the said alloy is beneficial with the proper control of alloy composition. So these are the optimal composition we have got by using GRA and Topsys. So, and based on analysis, which parameter is contributing more. So that also decided. So the predicted closeness value of Topsys is found to be higher as compared to J. When we compare both the things, so Topsys technique, the predicted, actually what we are doing is predicted values only. Comparatively, we see predicted value is very much closer in case of Topsys. So this is how the gradients also. Any other queries, please? you have any queries, you please feel free to ask the queries related to this the innovations in manufacturing sector. We have used the various materials, soapstone powder, graphite powder. Okay. Yeah, please. Anybody want to ask any question related to this manufacturing? Yeah. If anybody has any.
Thank you, sir.
Thank you.
Very good innovative session, sir. Thank you.
Oh, okay, sir. With this, we are closing the first session. Let us uh, continue for the second session also. Second session will be on the stress management and emotional strength, which will be taken by EAG sir from CSIF. Sir's name is GSR Raju. Is the current IG designated in CSIF. Is going to take the second session.